The James Webb Telescope is a giant leap in the history of stargazing. With its advanced capabilities, including its ability to peer back in time to the very first galaxies that formed after the Big Bang, the Supreme Observatory is expected to shed light on fundamental questions about the origins and evolution of the cosmos. However, more than 2 years after operation, the telescope, albeit solved a lot of puzzles, is raising big questions about the early universe. The data obtained by James Webb isn't just quite what scientists expected. So, though dazzled by Webb's stunning images of deep space, scientists had to admit that something was amiss. What the telescope has revealed contradicts scientists' current theory of how the universe grew up, and it's beginning to look as if we may need to rewrite the history of the cosmos and reshape humanity's position within it. Join us as we dig deep into how exactly James Webb just broke our universe in 2 years. The James Webb Space Telescope, as you know, is one of the most advanced telescopes ever built. Planning for James Webb began over 25 years ago, and construction efforts spanned over a decade. It was launched into space on December 25, 2021, and within a month arrived at its final destination, 930,000 miles away from Earth. Its location in space allows it a relatively unobstructed view of the universe. The telescope design was a global effort led by NASA and intended to push the boundaries of astronomical observation with revolutionary engineering. Its mirror is massive, about 6.5 meters in diameter. That's nearly 3 times the size of the Hubble Space Telescope, which launched in 1990 and is still working today. It's a telescope's mirror that allows it to collect light. Webb's is so big that it can see the faintest and farthest galaxies and stars in the universe. Its state-of-the-art instruments can reveal information about the composition, temperature, and motion of these distant cosmic objects. Thus, for thousands of space scientists, the James Webb Space Telescope is a window to that unknown universe. Just how far back can James Webb peer into the cosmos and into the past? Well, about 13.5 billion years. A telescope does not show stars, galaxies, and exoplanets as they are right now. Instead, astronomers are catching a glimpse of how they were in the past. It takes time for light to travel across space and reach our telescopes. In essence, that means a look into space is also a trip back in time. This is even true for objects that are quite close to us. The light you see from the sun left it about 8 minutes, 20 seconds earlier. That's how long it takes for the sun's light to travel to Earth. You can easily do the math on this. All light, whether sunlight, a flashlight, or a light bulb in your house, travels at almost 300,000 kilometers per second. That's just over 18 million kilometers per minute. The sun is about 150 million kilometers from Earth. That comes out to about 8 minutes, 20 seconds. But the farther away something is, the longer its light takes to reach us. That's why the light we see from Proxima Centauri, the closest star to us aside from our sun, is 4 years old. That is, it's approximately 40 trillion kilometers away from Earth, so that light takes just over 4 years to reach us. Or, as scientists like to say, 4 light years. Most recently, James Webb observed Earendel, one of the farthest stars ever detected. The light that the telescope sees from Earendel is about 12.9 billion years old. The Webb Space Telescope is looking much farther back in time than previously possible with other telescopes, such as the Hubble Space Telescope. For example, although Hubble can see objects 60,000 times fainter than the human eye is able, the Supreme Observatory can see objects almost 9 times fainter than even Hubble can. But is it possible to see back to the beginning of time? The Big Bang is a term used to define the beginning of our universe as we know it. Scientists believe it occurred about 13.8 billion years ago. It is the most widely accepted theory among physicists to explain the history of our universe. The name is a bit misleading, however, because it suggests that some sort of explosion, like fireworks, created the universe. The Big Bang more closely represents the appearance of rapidly expanding space everywhere in the universe. The environment immediately after the Big Bang was similar to a cosmic fog that covered the universe, making it hard for light to travel beyond it. Eventually, galaxies, stars, and planets started to grow. That's why this era in the universe is called the Cosmic Dark Ages. As the universe continued to expand, the cosmic fog began to rise, and light was eventually able to travel freely through space. In fact, a few satellites have observed the light left by the Big Bang, about 380,000 years after it occurred. These telescopes were built to detect the splotchy leftover glow from the Big Bang, whose light can be tracked in the microwave band. However, even 380,000 years after the Big Bang, there were no stars and galaxies. The universe was still a very dark place. The cosmic dark ages wouldn't end until a few 100 million years later, when the first stars and galaxies began to form. The James Webb Space Telescope was not designed to observe as far back as the Big Bang, but instead to see the period when the first objects in the universe began to form and emit light. Before this time period, there is little light for the James Webb Space Telescope to observe, given the conditions of the early universe and the lack of galaxies and stars. Peering back to the time period close to the Big Bang is not simply a matter of having a larger mirror. Astronomers have already done it using other satellites that observe microwave emission from very soon after the Big Bang. So, the James Webb Space Telescope observing the universe a few 100 million years after the Big Bang isn't a limitation of the telescope. Rather, that's actually the telescope's mission. It's a reflection of where in the universe we expect the first light from stars and galaxies to emerge. By studying ancient galaxies, scientists hope to understand the unique conditions of the early universe and gain insight into the processes that helped them flourish. That includes the evolution of supermassive black holes, the life cycle of stars, and what exoplanets, worlds beyond our solar system, are made of. However, data obtained by James Webb isn't quite what scientists expected. In the 2024 Isaac Asimov Memorial Debate, astrophysicist and science communicator Neil deGrasse Tyson moderated a discussion at the American Museum of Natural History in New York. The conversation was between scientists and surrounded the topic of how data from the telescope may be shifting our fundamental understanding of our universe. From discrepancies in the age of the universe to the unexpected brightness of early galaxies, the James Webb Space Telescope has already prompted scientists to reconsider how the early universe once operated, leading to revelations that could trigger major shifts in our models of the universe during the next decade or more of James Webb's tenure. And in the words of panelist Mike Boylan-Colchin, a theoretical astrophysicist at the University of Texas at Austin, the data from the telescope paints a consistent and consistently new picture of the early universe. The trouble began almost as soon as James Webb first peered into the distant universe. Webb's first views of such distant, ancient regions of space were confusing in two ways. First, some of its images contained huge numbers of galaxies. Far more, in fact, than astronomers thought possible so far back in time. Second, a handful of those galaxies appeared to be monstrously massive. These all dated back to the first 700 million years of the universe. And they were up to 100 times as heavy as scientists thought possible back then. For that reason, these galaxies were dubbed universe breakers. Our current understanding of how the universe grew up goes like this. First, dark matter collapsed into giant clumps known as halos. This happened within the first few 100 million years after the Big Bang. The halo's gravity then pulled in normal matter. This eventually formed stars and galaxies. This would have taken time. Matter would have clumped together slowly, eventually building up larger and larger galaxies. If true, the jumbo galaxies that James Webb spied so soon after the Big Bang shouldn't be possible. What's more, The current story of the universe doesn't predict nearly enough dark matter halos in the early universe as would be needed to build the many big galaxies that the telescope saw. In that light, things look pretty dire for scientists' current theory of how the universe evolved. The case of the surprisingly active early universe might be related to another well-known discrepancy in astrophysics, the age of the universe. The Hubble Space Telescope was a huge factor in helping narrow down the scientific consensus on the universe's age. In fact, the telescope's mirrors were specifically made to observe stars called Cepheids that astronomers can use to calculate that age. The resulting measurement of the universe's age, about 13.7 billion years, has stood ever since. But let's not forget, there is another way to measure the age of the universe. That's with the cosmic microwave background, the light from the earliest phases of the universe. Using this method, scientists came up with a slightly larger number, 13.8 billion years. And while that difference may not seem huge, some estimates using Cepheids are as low as 12.8 billion years. Worse, no one knows where the difference comes from. It's like we're digging a tunnel on opposite sides of a mountain, and we missed. Unfortunately, the surprisingly luminous early galaxies captured by James Webb did nothing to solve this mystery. In fact, the telescope's results led Rajendra Gupta, an astrophysicist at the University of Ottawa, to publish a paper suggesting that, based on the new data, the universe could be as ancient as 26.8 billion years old, about twice as old as current estimates. While the panelists agreed that Gupta's suggestion is extremely unlikely, the discrepancy of the universe's age in general does suggest the standard cosmological model and our understanding of the impact dark matter and dark energy have on our universe may need some revamping. Put simply, it could be that something fundamental is missing in our current picture. What's notable, the impossible early galaxies aren't even the only things that keep cosmologists up at night. The Webb telescope has double-checked the work of its older sibling, the Hubble Space Telescope. Hubble's measurements of the expansion rate of the universe are exemplary, the trailblazing observatory found, further ratcheting up the so-called Hubble tension. Putting it simply, measurements of the expansion rate of the universe, defined by a property called the Hubble constant, just don't add up. On one hand, observations of the cosmic microwave background radiation, which is like a baby picture of the cosmos from just 379,000 years after the Big Bang, say the universe should be expanding today at a rate of about 67.8 kilometers per second per megaparsec. This means that every volume of space a million parsecs across should be expanding at a rate of 67.8 kilometers every second. An alternative way to measure this expansion is by climbing onto the cosmic distance ladder, where each rung is formed by a different astrophysical milestone such as Cepheid variable stars and Type 1 supernovas. How bright these objects are can tell us their distances, which we can then compare to their redshift values to determine how much the universe has expanded while their light has been traveling to us. However, the problem is, this method gives us a completely different value of the Hubble constant, somewhere around 73.2 kilometers per second per megaparsec. The apparent paradox between the two measurements is what cosmologists have started calling the Hubble tension. Nobody knows what is causing it, but some hypotheses call for new physics to explain the apparent contradiction. One possible explanation is that there is a measurement error on the bottom rung of the cosmic distance ladder, which is home to the Cepheid variables. These are stars with luminosities that predictably fluctuate as the stars pulse in and out. The longer the pulsation period between moments of maximum luminosity, the greater that maximum luminosity is. This period luminosity relation allows us to accurately calculate their distances to Earth. It's possible to measure the pulsation period to calculate maximum luminosity. Then, based on how bright a Cepheid variable appears in the sky to us, we can work out how far away it must be to appear that bright. But it's not quite a foolproof method. The Hubble Space Telescope is able to observe Cepheid variables in distant galaxies, but the more distant they are, the harder they become to distinguish among all the other stars that crowd around them. As such, there was a concern that unresolved stars adjacent to Cepheid variables in these faraway galaxies were adding to the Cepheids' apparent brightness values, creating an unseen and systematic error in the measurements. Interstellar dust can also affect the brightness of Cepheid variables, dimming them from our vantage point on Earth. But new measurements achieved with the James Webb Space Telescope of 5 galaxies hosting a combined total of more than 1,000 Cepheid variables have ruled this possible error out. James Webb's infrared vision is able to cut through the interstellar dust, while its greater resolution allows it to clearly resolve the Cepheid variables so they stand out from the crowd. The 5 galaxies observed by James Webb, the most distant of which is NGC 5468, at 130 million light-years from us, have also hosted a combined total of 8 Type Ia supernovas over recent decades. These supernovas, which signal the destruction of white dwarfs, have a standardizable luminosity curve and form the next rung on the cosmic distance ladder above Cepheids. Because the preceding rung is required to calibrate the next rung, Webb's observations of Cepheid variables therefore makes the distance measurements using Type 1 a supernovae, which are bright enough to be seen in much more distant galaxies than Cepheids, more accurate. And they too tell us that there is a contradiction in the different measurements of the Hubble constant. From these Webb's measurements, astronomers led by Adam Rees of Johns Hopkins University determined that Hubble's original measurements were spot on. In the words of Rees, we've now spanned the whole range of what Hubble observed, and we can rule out a measurement error as the cause of the Hubble tension with very high confidence. What remains is the real and exciting possibility we have misunderstood the universe. We need to find out if we are missing something on how to connect the beginning of the universe and the present day. In other words, the tension at the heart of cosmology is here to stay. Physicists and astronomers are starting to get the sense that something may be really wrong. It's not just that some of us believe we might have to rethink the standard model of cosmology. We might also have to change the way we think about some of the most basic features of our universe. A conceptual revolution that would have implications far beyond the world of science. After all, there is no question that we have made incredible progress in understanding our universe, its history, and its origin. But it is also undeniable that we are profoundly puzzled, especially when it comes to the earliest moments of cosmic history. We have no doubt that these moments hold incredible secrets and perhaps the keys to a new scientific revolution. But our universe holds its secrets closely. It is up to us to coax those secrets from its grip, transforming them from mystery into discovery. In a recent remarkable finding, James Webb has discovered that early universe galaxies must have grown up way faster than expected. Plus, the same team also found that 10 billion years ago, the cosmos wasn't quite as disordered and chaotic as previously believed. The international team, led by researchers from Durham University in the UK, reached these conclusions by discovering evidence of structures called star bars, forming in galaxies that existed just a few billion years after the Big Bang. Star bars are elongated regions of increased star density found at the hearts of spiral galaxies like the Milky Way and other disk galaxies. As they form, star bars push gas toward the hearts of their respective galaxies, thereby regulating starbirth. The presence of these central bar structures thus indicate that a galaxy has entered a more settled and mature phase. As Zoe LeConte, team leader and a researcher at Durham University, said in a statement, "Galaxies in the early universe are maturing much faster than we thought. This is a real surprise because you would expect the universe at that stage to be very turbulent, with lots of collisions between galaxies and a lot of gas that hasn't yet transformed into stars. However, thanks to the James Webb Space Telescope, we are seeing a lot of these bars much earlier in the life of the universe, which means that galaxies were at a more settled stage in their evolution than previously thought. This means we will have to adjust our views on early galaxy evolution. Notably, this isn't the first time scientists have gone bar hopping in the early history of the 13.8 billion year history of the universe. The Hubble Space Telescope witnessed these features as well, but that orbiting eye on the universe could only go as far back as 8 billion to 9 billion years. However, the increased sensitivity and wavelength range of James Webb has stretched such observations back at least another 1 billion years. This has revealed bar formation in galaxies that are seen as they were between 8 billion and 11.5 billion years ago. In fact, of 368 disk galaxies the team considered for the study, 20% already had bars. That is double the number observed by Hubble. The further back in time the team looked with James Webb, the fewer bar structures they observed in galaxies. They believe this could be because galaxies at earlier stages of the universe were not as well formed. An alternative may be that shorter bars were more common in progressively earlier galaxies. Even the impressive observational power of James Webb isn't sufficient to see these short bars in early galaxies. With these results in hand, the team now wants to use the telescope to peer even further back into cosmic time, looking back as far as 12.2 billion years ago. This could reveal whether bar growth was common just 1.6 billion years after the Big Bang. As Gaudotti concluded, the simulations of the universe now need to be scrutinized to see if we get the same results as the observations we've made with the James Webb Space Telescope. We have to think outside of what we thought we knew. In another observation, the Webb telescope has discovered the oldest dead galaxy ever seen. But the cosmic corpse has left scientists puzzled as it defies explanation by our current knowledge of the early cosmos. The galaxy suddenly and mysteriously halted star formation when the universe was just 700 million years old, when countless stars were birthing thanks to an abundance of pristine gas and dust elsewhere in the universe. The galaxy, named JADES GS Z701QU, and described in a paper published in the journal Nature, provides astronomers with a peek into the elusive underpinnings of galaxy evolution in a primordial universe, including why galaxies stop forming new stars and whether forces driving their starbursts alter across epochs. In the words of study lead author Tobias Lusser, a researcher at the University of Cambridge's Kavli Institute for Cosmology, Cambridge or KICC, galaxies need a rich supply of gas to form new stars, and the early universe was like an all-you-can-eat buffet. Current models cannot explain how the newfound galaxy not only took shape in less than 1 billion years after the Big Bang, but also shut down its star factory so quickly. According to study co-author Francesco D'Eugenio, also a researcher at KICC, it's only later in the universe that we usually start to see galaxies stop forming stars. In comparison, a handful of other dead galaxies found elsewhere appear to have paused forming new stars when the universe was about 3 billion years old. To discover JADES GS Z701QU, Lusser and his colleagues used James Webb's powerful infrared vision to peer through the thick veil of dust obscuring the earliest objects in the universe. In addition to being the oldest dead or quenched galaxy spotted so far, the newfound galaxy is also many times lighter than other similarly quiescent galaxies previously found in the early universe. Webb's data suggest the galaxy intensely formed stars for somewhere between 30 million to 90 million years before it rapidly shut off, although precisely what ended it is still unknown. Astronomers know of a couple different factors that can slow down or extinguish star formation. For instance, turbulence inside a galaxy, such as radiation emitted by a supermassive black hole, can push gas out of the galaxy and starve it of the gas reservoir it relies on to form stars. Another intriguing possibility is that the galaxy's surroundings at the time did not sufficiently replenish the gas reservoir being consumed by birthing stars, leading to a deficit in star-forming material. However, in the words of study co-author Roberto Maiolino, an astrophysicist at KICC, we're not sure if any of those scenarios can explain what we've now seen with Webb. Current models based on the modern universe are unable to explain the properties of JADES GS Z7901QU, suggesting they may need to be revisited. Another possible explanation for the new galaxy's dormancy could be that galaxies in the early universe die and then burst back to life. However, previous research of dead galaxies from when the universe was around 3 billion years old, a time of its most prolific star birth, suggested such dead galaxies cannot rejuvenate even via mergers with nearby galaxies, which instead only serve to puff them up. As Eugenio said, we'll need more observations to help us figure that out. A quick note, James Webb now is digging deep into the mysteries of gas planets. More specifically, the researchers say they've started making headway in answering the question of how long gas giants likely have to form around their host stars before all the gas around those stars fades away. The short answer is not very long, but the full story is far more nuanced. The research team used the Webb telescope to probe what's a little confusingly known as the disk wind. This doesn't really refer to a wind like you may imagine. Rather, it refers to the process of gas leaving a disk around a star. This disk would be one filled with different types of material with the potential to give rise to planets. It's thus otherwise known as a protoplanetary disk. According to Naman Bajaj, lead author of the new disk wind analysis and a scientist with the University of Arizona's Lunar and Planetary Science Laboratory, we knew that they exist and that they might play an important role in disk evolution. What we didn't know was the underlying physics, and consequently, how much mass is being lost. These are key to answering all our questions on its impact. Such a disk would include non-gaseous debris too, to be clear, like dust that can come together over time to create rocky planets. That's actually how Earth is believed to have formed once upon a time. Though Bajaj and fellow researchers didn't come up with a final, tightly confirmed answer as to how long gas planets may have to form before protoplanetary disk gas depletes fully, he did offer a ballpark based on his calculations. According to Bajaj, considering the gas mass in this disk, and assuming that the gas will keep leaving at this constant rate that we find, about 1 moon mass every year, it will take approximately 100,000 years. Yes, that sounds like a long time. But, as Bajaj emphasized, it's an incredibly short timescale in astronomical terms. A protoplanetary disk lives for about 5 to 10 million years. After all, though it's severely cliché to say at this point, all of this is a testament to how much the James Webb Space Telescope is revolutionizing our understanding of the universe. Its infrared sensitivity is immense for sure, but a lot of its discoveries owe themselves to the body of work already available to build on. The library of papers that's been helping scientists decide where, precisely, James Webb should look. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.